Hey guys, we're Group 8. Our project is simulation of swarms of unmanned ground vehicles. I'm Carter Nichols. My major is electrical engineering.
I'm Chase Gallo. I'm studying electrical engineering.
Charles LaFleur. I'm also studying electrical engineering.
I'm Jesse McDonald, and I'm studying computer science.
I'm Jefferson Charles, and I'm studying computer engineering.
Our project summary. With the advancement of drones and their swarming capabilities, new challenges emerge, such as the need for reusable and adaptable swarming software. Additionally, variations in robot designs within a swarm necessitate cross-platform compatibility using the same software. Packages like ROS2 Swarm address these issues by providing a reusable solution for robot swarming. Our proposed solution. Implement ROS2 Swarm to enable a decentralized robot swarm that can perform collaborative tasks in both simulations and with real live robots. This will facilitate complex behaviors such as aggregation, which has robots coming together, dispersion, which will have them moving in different directions away from each other, and collective decision making, which would be a voting pattern where the robots will choose a direction to go and vote on it and collectively go in that direction. This will explore the dynamics of autonomous cooperative behaviors, providing insights into scalable swarm intelligence, which is things like the swarm limits, how many robots we can control in a swarm, as well as how much information can pass at any given moment to this amount of robots.
So here's our system overview. We're going to have our laptop, which is our host computer, which is where the user interface will be. It'll also be where commands are executed to control the robots, check the status of the robots and check communication lines. Communication to the robots will be established via the Wi-Fi network. The DaVinci Lab in EE has its own dedicated ROS local network set up where these turtle bots can connect to and our host computer can connect to, therefore creating a medium for us to communicate.
All right, so there's two main robots in this project, the turtle bots and the dingoes. The turtle bots will be the primary robots we will be implementing on, while the dingoes will be implementing on if we have the time. We would like to implement on both of these robots to demonstrate ROS2 Swarm's ability for cross-platform across multiple robots. The LiDAR enables environmental perception, and that will be used for 2D mapping and obstacle avoidance. The Raspberry Pi is the main processor, which is used to determine commands and obstacle avoidance and facilitate ROS topics. It has a built-in Wi-Fi module, which connects to the local network, which is how it communicates to the host PC. It will run on a Linux-based operating system, Ubuntu. The version of Ubuntu depends on which ROS distro is desired. And then there's the OpenCR, a microcontroller, which is designed specifically for robotic applications. And it's the central control unit that facilitates many of the essential functions, such as motor control, sensor integration, power management, and more.
So here's our TurtleBot subsystem design. Here's our block diagram on the right. So the communication with the TurtleBots would be set up by a Wi-Fi. And so the antenna, which is built on the Raspberry Pi, will be the main line for communication. The ROS master node will be the central point of communication within the TurtleBot. It will be the main node in which everything communicates through. The TurtleBots use the publish and subscribe method, which is where a component will publish data to a topic, and if another component needs data from that topic, then it will subscribe to that topic. There may be multiple publishers and subscribers for one single topic, but none of the publishers and the subscribers are not aware of each other's existence. The master node will be an access point that will set up the connection between the host computer and the topics the Turtlebots will publish to.
Another subsystem we have is the Rost Swarm subsystem, and this will be running all our swarm voting behaviors on each robot independently. And the flowchart block diagram to the right shows the different parts of the robot and how they interact to produce the desired swarm behavior. And like I said, it's applicable to all robots, especially or as long as they have a LiDAR and motors. The Rasta Swarm subsystem steps, it first starts by a user initiating a desired swarm behavior. And secondly, the robot checks its surroundings through its LiDAR and calculates a drive command that would need to be executed. But before the drive command is actually executed, it goes through a hardware protection layer, which checks from the LiDAR data if there's any possible collisions, if our movement pattern were to be executed. And if there is a collision, it'll send an adjusted drive command to the motors to avoid any collisions. If not, it'll just proceed with the normal drive command that was calculated before. And so finally, the drive command goes to the motors, the robot executes it, and this cycle is repeated until the entire swarm completes its behavior. The interaction this subsystem has with other subsystems is that it directly interacts with the Turtlebot and Dingo subsystems, as those robots will be executing the swarm commands, and it also uses the LiDAR data from the robots to calculate position and orientation, as I described previously, and also directly publishes commands to the motors. And lastly, it interacts with our ROS to ROS2 bridge so that our robots could use ROS to swarm commands, which Carter will be talking about next.
So the ROS to ROS2 bridge will be primarily implemented on the host computer. This is kind of needed because the ROS bridge is limited to only devices that have both ROS and ROS2 set up. Since the Turtlebots run on ROS Melodic and the host computer is going to be running on ROS2 Foxy, this bridge is needed to facilitate communication between the two. This is also kind of needed for any kind of cross-platforming that you're going to do. If you have a robot that uses a different version, you're going to need some form of bridge to facilitate any kind of communication between the host and the robot. So our ROS bridge will be set up using a publish subscribe method. And what it will do is it'll subscribe to a ROS1 topic on the robot. And so it receives the information from that topic. And then it's going to publish to the ROS2 node on the host computer. And what it's going to do, it's going to change any commands from ROS to ROS2 that are needed. And then it'll send the data to the node on ROS2. And so our references primarily come from the ROS2 Swarm package, which they wrote a research paper on and posted into the IEEE conference, and also some GitHub repos that discuss ROS2 Swarm and ROS Bridge.